So here's one of the systems that I've modeled. So this is actually one compression phase with 3 different generation phases modeled at the same time. If we look at the compression phase, we basically have a compressor that is pressurizing a tank. Now, if we start on the left side, there's an input signal going into the compressor, and that's really you can think of it like a plant control system where you're controlling the mass flow of the compressor. And all I've done is I have set the mass flow rate to be 100%, and as the pressure in the tank builds to the pressure that I want, I've dropped it down to 0. So the other input to the compressor is the substance itself, which here I've modeled as air with some humidity. And if we take a look at the compressor, we see that we've modeled it isentropically, and so we've set an efficiency and a maximum mass flow rate. And actually, if you wanted to, you could model it in different ways. You could take a polytropic assumption, you could call it a mechanic compressor, or an active compressor. Now, an active compressor lets you, if you feed back the downstream conditions into this compressor, depending on the compressor map, it'll actually calculate the instantaneous efficiency and power depending on what the RPMs, the downstream pressure, and the upstream pressure are. So that's kind of a nice feature to use. But here again, we're using isentropic. Now the outputs of the compressor are the mechanical power, and here I just have used a tag. So I'm constantly monitoring the power that's being consumed by the compressor at every time step. And then the output flow is going into this isobaric process. Now I've added that because it's important to control the temperature going into the tank. And then if we look at the tank, I've modeled it isothermally. So again, because I really want to control the temperature of that tank, to not have hot air inside the tank, and then as it cools, it could, you're going to lose a lot of pressure for generation. So you could model it adiabatically as well. And then some of the parameters are, for example, tank volume, and then you can also edit some of the initial conditions, such as initial temperature, initial pressure, and the composition. So here I just have air. And then the last step is actually, so if we move on to the next generation phase, I have here a simple cycle gas turbine system where the tank itself is depressurizing, and that is that flow is fed into a mixer, and so that flow is mixing with an input of natural gas, and I've set, I believe here, 3 kilograms per second of natural gas input, but I've also optimized that based on the inlet temperature to the turbine. So of course there are mechanical limits to the turbine, which are driven by that temperature. And so after the flow goes from the mixer, it goes into the combustion chamber. And here it's just a simple reaction where methane plus oxygen ends up being water plus CO2. And after that, the flow goes into the inlet of the turbine. I've also set the outlet pressure of the turbine to basically be ambient air. So it does an isentropic calculation, and so I have set some efficiencies here for the turbine. And then the output is the mechanical power. I've added a second tank. And the second tank is essentially modeling what the OCAES system would do, where you eliminate your throttling loss and your output is at a constant pressure. So the second tank has a very large volume, and it's filled with water. And so as the air tank depressurizes, it's going to get backfilled with water to maintain that pressure. And I also have some monitoring as well, that just to make sure that the output pressure is staying constant. Now after that, the flow is going to go into the mixer, and then into the combustion chamber, and then the turbine. So that's really the primary differences between the two systems. Now, for the last system, what you're going to end up with, or what I've done is, I've actually added a heat exchanger, what's called a recuperator. So we're capturing the exhaust flow of the turbine and then feeding that into a heat exchanger and preheating the incoming flow that's going into the turbine. And so what you end up with is much higher efficiencies. Now, for the heat exchanger, you can actually model it in a few different ways. So here I've got a counterflow heat exchanger, but just as well you can have a cross-flow or a parallel flow heat exchanger. And then you're going to need to determine what some of your constants are. So for example, you're going to need a heat transfer coefficient. You need, if you want to have